Right. Yeah. So hi everyone. Thank you for coming here remotely. As Florian said, also my main research is about core message actions. I'm going to talk today about the IMAP and collaboration, specifically the 3UCubed CubeSat project, which is work that is done by quite a few mentors listed here. It's about Noé Lugaz at Sonoma State, Mark Lissard at UNH, Marcus Alfred at Howard University, Sonia Smith, which is not the UNH Sonia Smith, at Howard, Gary Jernigan, which passed away, and Lynn Kaminsky, and then Sanj Mehta being the main engineer, and Doug Clark. And then most importantly, probably by now 40 or so students at UNH, Sonoma State, and Howard, which I started listing on this slide, but there were just too many names, that's too much. So most of the work I'm going to talk about and present actually is from students. I'm trying to give some names. So first, what is student collaboration? It's something relatively new, but not that new anymore. It's required since maybe about 10 years or so by NASA for now all missions. And there's a 2018 NASA Science Mission Director, SMD, memo from Zolbuchen listing what this student collaboration should be. It should be hands-on opportunity across the life cycle of a flight or instruments performed by a student. And that's a relatively vague statement. So there's been quite a different ways people interpreted what should a student collaboration be. From one end, there's kind of the Lucy, which is a planetary mission, did this quite nice L-space program, which is almost purely educational driven. It's actually some kind of online school where they reach out thousands of students, actually gives them introduction to mission design and mission and NASA work, but not really any hands-on experience in building things. And then especially I think for smaller missions on IMAP, IMAP is a flagship, $500 million or a bit more mission. For smaller mission like mid-axis or SMEX, often the student collaboration is kind of science-driven, I feel, in what is being built. And often it's an instrument that either would scope or an instrument that will provide some nice science on the main mission. And I think the first example from this was New Horizon, which has a dust counter, which I think I've heard was actually descoped early on, and so came back as a student collaboration. But in some sense, it's not that different from what Helios Swarm is doing with Electron ESA, which will be built at Berkeley, and Punch, SMEX to be launched, I think next year, is doing with the SEAM high energy detector. And what we try to do for the IMAP student collaboration is kind of a mix of this both approach. We try to give a science-driven, hands-on experience to the student while still giving quite a bit of education and outreach. And so we're not reaching as many students as L-Space from Lucy, but at the same time, we're probably reaching more students than the science-driven one will do. So what are we doing? Our goal is to augment IMAP science and also develop hands-on research experience for students, primarily undergraduate, and to contribute in a small way in diversifying space science. And so I'm going to talk mostly about the CubeSat today, but really the student collaboration is not the CubeSat, and something I have to remind headquarters and a bunch of people all the time is that it's really a multi-aspect program. We have this CubeSat project, which is a collaborative hardware project between UNH, Howard University in DC, and Sonoma State in California. After we launch, we are hoping to have joint analysis of IMAP data with student collaboration CubeSat data, but we also have a kind of a retention recruitment education program for the students with an online community, which was planned before COVID happened and kind of was good because when COVID hit, so it's kind of a beginning of our program, and we already had planned for online community because you have two university and thousands of miles apart. And then a strong evaluation component. We have an outside evaluators that interviews the students when they join throughout the programs and when they finish either by graduating or decide to stop and do something else. So what is it that we promised to do? It was a bit strange. I'm not going to go into the details, but because IMAP was selected without a competitive phase A, and the student collaboration was supposed to be evaluated at the end of this phase A, we're kind of in a bit strange situation where we wrote this during the main proposal of IMAP, were not fully evaluated, and then got carried on when IMAP was selected without phase A, without competitive phase A. But there are 6 top-level requirements, which are not CubeSat requirement, obviously. These are really what this program is trying to do in terms of education, hardware, and so on and so forth. So we want to build one CubeSat with at least one student-built instrument and deliver it before the launch on IMAP, launch it before the end of IMAP prime mission. So IMAP is expected to launch in early 25, and of prime mission will be about 2.5 years later. We want each student at each of the 3 universities to have participated in design and build of either an instrument or subsystem. And we'll give some number. We're expecting to reach about 35 students, which is a number already reached, including 50% of underrepresented minorities or women or in STEM. We're tracking the student progress, not only in the program, also towards a degree. We want to make sure they're not, taking too much time off their classes to work on a hardware program and things like this, and we evaluate it. So really, because it's a partnership between 3 universities, what we decided to do eventually is to build 3 engineering models, one at each university, identical engineering model. That's kind of the stage we're at right now. And then following CDR, hopefully at the end of this summer, we will build one flight model that will be delivered towards the end of 24 for launch. And it's really it's really a program centered on undergrad students. So we have one grad student, Jenna, at UNH, but pretty much every other of the 40 or so students being involved are undergrad. So from now on, I'm going to really kind of fully go into the CubeSat, which is called 3UCubed, which now we spelled, but like take less space when I put it as a cube here. And the idea was just we have 3 universities, we're doing a 3U CubeSat, and we're trying to study atmospheric upwelling, I'll discuss, and uplift undergrad. As I said, the design, which has been a lot of the things that I've been trying to, from the beginning, give to the students, something that I feel students don't necessarily have occasion to participate in, is really a mission design. So they were not given a mission that had any subsystem selected or so on and so forth. So they spent quite a bit of time, almost 2 years at the beginning, doing the primary design and so on and so forth, which is something that students don't really learn usually, even in CubeSat project, and can be challenging because it's not really hardware, but it's something that is very much needed, I feel, and gives them quite a nice experience. So we're building 3U CubeSats. As I said before, our goal is to build 3 of them. Each university will build 1 EM, and then we'll build 1 single flight model based on what we learned from the 3 EMs. I'll go into details, but we have 2 instruments which have about 1.5 U, so half of the size of the CubeSat, and we want to launch. Our success is to launch 1. So what is the science this CubeSat is going after? So trying to go after is atmospheric upwelling, specifically in Earth's cusp region. And kind of the scientific justification really is that there's been one reported now from Champ and Grace and other missions that you can get quite large, is what's on the left-hand side here, quite large change in the atmospheric densities at low Earth orbit, where many satellites are now, from the starting constellation to OneWeb, and we have literally thousands of satellites now in low Earth orbit, whereas atmospheric density can pretty much change by order of magnitude, which is a primary effect on drag and on lifetime of satellites and potentially collisions. And specifically, that's what's on the right-hand side here. if you look at where do you have the largest kind of density increase for satellite in polar orbits in sun synchronous, which will be one of the Starlink next shells, the biggest increase you get in density, in atmospheric density, is really in the cusp region. Partially probably from electron precipitation, maybe from joule heating, and kind of associated with the atmosphere heating up and upwelling, so you get higher density at a given altitude. I think most of you have heard about the SpaceX, pretty much 1 year ago, almost to the day now, loss, when they launched, for economical reasons, they decided to launch spacecraft, about I think 50 of them, at the same time at very low Earth orbit, about 200 or so kilometer, where the lifetime is pretty much less than a day. And then as the satellite rise into a stable orbit at 500 or so kilometer. And what happens, there was a very minor storm, but enough density increase that SpaceX lost 40, a bit more 40, 80% of the satellite that they launched on that day. And so they already mitigated. Now they're launching at slightly higher altitude, where they launched, I think, 4 or 5 less spacecraft. But that's a clear example that atmospheric density and the change of it, especially during storms, can have a critical effect on satellites, which is really what we're trying to study. So look at what are requirements in terms of the science of the CubeSat now. We kind of have 3. We want to characterize the neutral density in the polar region and the cusp. We want to characterize the variation of this density, and we want to characterize the local plasma properties. So that's requirement 7 to 9. And our science questions really are science objective. In more details, characterize neutral atomic oxygen, which is a primary atmospheric element at altitude of 400 or so kilometer in Earth's orbit, on spatial scale of about 20 kilometer, and characterizing electron precipitation, which is one of the main proposed causes for this upwelling for energy, but below 200 eV, because that's kind of the energy from maybe 20 to 200 EVs as a critical one, where energy is deposited at this kind of altitudes. I'm going to pass on the flow down, but so again, a lot of this is developed by students doing a flow down, which is something, again, not really taught in class, especially not at undergraduate level, neither at UNH, Howard, or Sonoma State, but how to do a requirement flow down is something we spend quite a bit of time trying to explain to the students. And so kind of our objective, partially written to match 2 instruments that have launched before on rockets by Mark Lessard. One of them is a photomultiplier tube, ultraviolet photomultiplier tube here on the left-hand side. Kind of the bottom curve here is so UV light measured during a rocket flight on Renew 2. Bruce Fritz, which was Mark graduate students and now at NRL, is the one kind of wrote the UV PMT paper. So that look at UV light, which is directly caused by neutral atomic oxygen line in around 148 or so nanometer, allow us to characterize atomic oxygen. And then to look at electron, we decided to kind of modify an ARPA, which used to be to study thermal electrons, but modified to study energetical electrons. This flew a number of rockets from Mark. I think from the first paper from Jan Cohen, one of Mark Lessard grad student now at APL. And so kind of those are 2 instruments that kind of relatively low mass, low volume, and low power, so quite adequate for a CubeSat. So it's actually here shown in the rocket version, the ARPA on the left and the PMT on the right-hand side. PMT is here on the bottom mounted here. So we change a bit. The PMT had the least number of change, the photomultiplier tube. Most of the change was really in terms of the form factor and the backend electronics. The ARPA, we kind of redesigned it significantly because the design for rocket is to look at thermal thermal electrons, so few electron volt, which we decided that most likely we won't be able to observe them because of spacecraft charging. So we found it was much more safe to go after energetic electrons because probably we'll be able only to observe things above 20 to 30 eV, maybe. We also kind of change the field of view slightly. I'll show you some of the updates. And so pretty much now, everything I'm going to show you was done by undergrad students. Some of them are in the room probably. Some of them actually have graduated since. So there are the CADs of the two instruments, so the separated ones. So on the ARPA here on the left-hand side, and the PMT, so actually the photometer tube itself is here on the bottom. So just the entrance system. And so the big change we made is that we created a common electronic boards, so a power board and a signal board here, common between the two instruments that pretty much have been fully redesigned by first by Jeff Campbell, that graduated last year, taken over by Sanj, and now is being worked on by Matt Roland, Caden, and I forget. And Matt, oh yeah. And so one of the things we changed also is we decided to add microcontroller on the instrument, that it can be worked independently a bit on the onboard computer. It wasn't really necessary, but felt was the most flexibility for our design. And finally, we have this additional board here, which is just a PC104 board that allows to slide this into the CubeSat and connect to the onboard computer. So this actually was for PDR, so just showing kind of the view of the instrument. I think Sanj, as you can see him from here, as the model CubeSat in front of him, and or not? No, he has a bottle in front of him. You have a bottle. Your bottle confused me. So it's actually here. We have the engineering model that doesn't have the boards yet on that version, but just to show you what's inside. There'll be a photometer tube, which is not there yet, and then the two boards, signal board, power board, PC104 board, and then pretty much the shielding. So the big thing we've been doing in the past 3 or 4 months is kind of trying to go from the design of the board that was done pretty much finished maybe 6 months to 1 year ago now, into actually building the boards. So what the students are doing in the second floor, and then down in the shop is setting up this board, baking them, and then trying to figure out that a few things had to be modified. They're quite busy. We have the PMT takes 800 volts to get take 800 volt, and then the ARPA is modified to measure 150 electrovolt electrons, so needs 150 volt power supply. So we have some so-called high voltage and not really high voltage. The high voltage by definition, but barely. On this board, which is quite busy. That's the anode for the ARPA. So it's a lot of things that electrical engineering students are doing on the group, setting this up self. And then thing that doing the computer science student is kind of learning how to interface directly with STM32 microcontroller for the instruments. So Jared and Shane here, and Helly and Erica doing this quite a bit. So enough for the instrument, just what is our basic of concepts operation. So again, one of the main target area is a cusp region. So we need to go to the cusp. So we need to have a quite an inclined orbit. So that's one of the main requirements is we need to go into polar orbits. We want to have enough measurement to get enough altitude to get about 6 months of measurements, plus maybe 1 month of commissioning. So that's an altitude probably at 425, maybe even 450. We're going to launch in SolarMax. That's our goal. And so in solar maximum, there will be much more flares and the overall atmosphere will be heated and lifted. And so we have to be a bit careful with the lower altitude we want to get because you can get quite quickly into an orbit that deorbit very quickly. So we want to rise this 400 to 425 most likely. And on the other hand, I don't know if all of you know, but the FCC just maybe a few months now passed a requirement that missions should deorbit in 5 years after the end of the mission. This is a change from a previous requirement that used to be 25 years. And so that kind of restricts a lot how high we can go. Probably 625 is kind of the limit if you want to get 5 years. And so it's a pretty narrow range now, unless you want to get an active deorbiting mechanism on the CubeSat, which we're trying to avoid. But in terms of getting our science and getting the orbits, sun-synchronous orbits, similar to what tracers is going to go into, or what DMSP, but at lower altitude is going, would work. So kind of common launch, common orbit at 500 kilometers. So that's something we should be able to get. In terms of the concept of operation, the idea is really that instrument will only be on when we are at high latitude, so above about 60-degree geographical in the auroral region and the cusp. The cusp is pretty narrow. It's only a few degrees in extent, but it can both move in local time, in magnetic latitude, and then magnetic latitude itself change in terms of geographical latitude depending where it is. But we're going to do this purely based on the predicted orbits and the TLE. Life is much easier if you're doing CubeSat, if you don't have a GPS, in terms of NASA is very careful now about safety. So if your mission has propulsion or if your mission has GPS, you need to make sure that it can be hacked. And so we found it much easier. We found much easier to design a CONOPS that doesn't require a GPS to know where we are. So we're going to turn the instrument on when we know we're at 60 degrees, leave it on throughout the polar region, take measurements and downlink them. And that's few enough measurements at a cadence of a tenth of a second or so to get about 1 to 2 kilometer resolution that we can work with UHF radio, which makes it also much easier and much cheaper, and potentially doing with a amateur radio on the ground. So the system is here on the left-hand side. We're trying to keep it simple. No deployable solar panel, just onboard computer, attitude control, being made to torquers. Kind of the most complex thing is an antenna, which we'll buy off the shelf, which is deployable. And then our instrument takes kind of the top 1.5 U. And so again, even though this block system has been done by students. So kind of implied here is we're trying to get almost everything off the shelf, commercial off the shelf parts with flight heritage. So the bus that we decided to go with is Androsat. So we get the structure, solar panels, the onboard computer with it, the radio and the antenna. We'll go with this attitude determination and control system from CubeSpace most likely, which would have 3 torquers and 1 reaction wheel for added flexibility. We don't need the reaction wheel itself, but I think it will just give us more flexibility during the mission if things go wrong, or if we want to target a bit more precisely something. The last thing we have to get is to finalize is the EPS, the battery and power board. We're most likely going GOM space, but the main issue is it's a 5 months lead time. So if you order it today, we'll get it in July. And so we're trying to see this anything which is as much lower lead time. If you're in hardware, you probably know that lead time is a big issue right now. I know since COVID, there's a lot of parts, electronics parts are hard to get or to get quickly. We have students, mostly MEs. Right now, it's Matt Champagne. I think Emily did some, and Kaden. Doing the CAD and then the thermal. So we have about a kilogram of free mass, even when we have include contingency. This dot here shows center of mass, center of gravity is actually decently placed right now. We can have 1 kilo to play with if you want to make it a bit more central. And one thing that was kind of a struggle to teach students is to do thermal. It's not something students learn in undergrad level, at UNH at least, and at Sonoma and at Ward. I'm sure someplace they do learn it. But so it's learning ANSYS and thermal desktop was quite a struggle. And some students were here and learning it because we need to update that. But for PDR, Delta PDR, we perform both a steady state hot simulation. So that's the one on the right-hand side here, showing when the spacecraft in full sun, making sure that temperatures are decent, and it is. It's about 30 degrees Celsius max, which is well acceptable. And then because in orbit, we're going to spend about 40 minutes in eclipse, making sure the cold side works. So you cannot really a steady state cold side. You need to do a transient model. So that's a very simple model where we started at 0 degree and see what happened in 30 minutes. So the scale should change here, but because I should run to because I did a cut. So after half an hour without sunlight, you get pretty much the coldest part of the structure at minus 50 Celsius, an internal component somewhere between minus 15 or minus 10 to minus 30. We have to be, maybe need some power heaters next to ADCS. The battery will come with our own heaters. But again, we have quite a bit of power, mass, and volume available. Again, 1 kilo, about half a U, where we can put some heaters. But that's something that students, that's one of my main tasks I'd like to get before CDR, is making sure we get the thermal up to date and getting sure that the power budget is done accordingly. So kind of to finish on this, we really try to keep simple. Actually, the model on the right-hand side is an older model. We had fixed solar panels, so there's 2 3Us on the side, 1.5 U next to the instrument, 1 U on the small side, and then 2.5 U on the back because you need to leave some opening for the Earth sensor and the radio. The only deployable is going to be the antenna, that's an older version, and pretty much everything is CUTS, commercial off the shelf, except the instrument. And again, we're leaning towards a slightly more advanced ADCS system, but everything else being very simple. So when we proposed to IMAPs, with IMAP as an IMAP collaboration, the very first meeting I had with Nikki Fox was the project scientist at the time, Dave McComas, the PI, and Nathan, the deputy PI, was one thing that NASA judged during collaboration is how much risk do they put on the main mission. And so I think Dave had decided, well, if we make a CubeSat that launched separately from IMAP, there's absolutely no risk for the main mission. So he was very happy with this, and so that's what we decided to do. So we're not launching with IMAP. So when we proposed it initially, we didn't know how we would launch, but a year and a half ago, a bit less, in November of 2021, we proposed to the yearly call of NASA, called the CubeSat Launch Initiative, CSLI. We were selected. It's actually becoming quite a bit more competitive. I think about 35% of the proposal got selected only last time. I think 6 out of 18 or something like this. And basically what it does is, so we'll provide you a launch. As long as you're less than 3U, we no cost for you. So that's to launch one spacecraft, one 3U CubeSat, the one flight model will do. Currently, we're hoping to launch, to deliver at the end of 24, to be launching almost the same time as IMAP, if all goes well, in early 25. And we still, somewhere in the back of my mind, I'm hoping that the other universities will take their engineering model, which would be almost the same as the flight models, and apply to CSLI and get the expertise of applying to CSLI, applying to the FCC for licensing, applying to NOAA for licensing, and so on. But want to make this clear that it would be great to have a 3U CubeSat constellation in the cusp, kind of like a mix between Firebird and tracers. But we're not proposing this. We're proposing one CubeSat to be launched. So even if we launch multiple, which so far is not the plan, we'll not be coordinating. Sonoma State, because I actually did already 2 CubeSats, one successful and one that lost. We never make contact with it, but probably because of the CubeSat antenna. As a ground station, one the plan is that Howard University will build one, and maybe we'll build it at UNH. But there's already a ground station that works at Sonoma State, so that A, we can learn from them about how to operate and build one for students, and then B, we can pretty much, all the plan is the CubeSat will be able to be operated and all the data downloaded from this one ground station in Northern California. Just to finish on this, kind of where are we at? So that's the picture. Pretty much should be very similar to what's around in the room. That's the actual structure, the UnderSat structure. So that's actual engineering model. The instrument inside doesn't have the boards, so it's kind of an empty shell at this stage, but that's what we're working on. And then we have the onboard computer, we have the radio. We just need to get the DCS and the EPS. Meanwhile, sorry for all the computer science and engineer in the room, but it's very hard to show what the work they're doing, and it's a lot of work developing flight software and developing instrument software. I think it's been quite a bit of experience for Sean and Jared to learn how to kind of code directly this STM32. But so they've come up with kind of the testing protocol for the instrument, how to test the analog to digital converter, to make sure we get all the housekeeping data that we want, the different voltages and temperatures. And meanwhile, one thing that probably we're trying to spend more time and effort on it that you do on rockets is on calibration. Typically, instruments for rockets are not calibrated as carefully as for CubeSat or space mission. So one thing that Kelly has been doing is kind of developing the UV-PMT calibration protocol. So I'm showing you on the middle is actually the CAD of the PMT calibration. We have both a UV source. I think we ordered some filters. We're supposed to have a calibrated photodiode, but there's no calibration for the next 6 months or more, 9 months or something like this. So we're gonna have to do with what we get. But I think she has to get this done before she graduates in a few months. But I think she'll be able to get the full calibration setup and probably running the first calibration run for the UV-PMT before she's done. And then Adri, which is in this room too, I think, is gonna. And Jenna probably are going to take over on the ARPA, calibrating with electron gun and probably vacuum chambers that we get from Mark. So kind of a summary on this, in 10 more minutes, I can give you some thought about a larger mission. We have 3 university building, 3 EMs, 1 EM each. That's pretty much the stage we're at. I'm hoping to get the instrument CDR kind of early in the spring, let's say, and then the mission CDR probably in the first few weeks of September. And then it's much less work than a big mission in terms of integration and testing. I mean, still a lot of it, but we would have the flat sat at this time. We can start to test the flight software, and so the goal is to deliver for CSLI at the end of 2024. It's pretty much almost the simplest system you can think of. Fixed solar panel, UHF radio, no GPS, everything is off the shelf. The only thing which is deployable is the antenna, which is as a fail-safe if it doesn't deploy. And then, we are still finalizing the exact orbit we want, but I think most likely in terms of what NASA would give, we'll get probably a sun sync or near sun sync orbit. And we just want to make sure the altitude is good enough for us to stay between 6 months and 1 year, and not too good for us to stay more than 6 years. And the pretty simple ConOps or the instrument is on above 60 degrees, not being commanded, purely based on TLE. That's all I have on this CubeSat. So if you have questions on this, I can take it now, or I can talk to you more, but general thought I have on larger missions.
Is there any question on the CubeSats? Yeah, sure.
No, what do you do for power?
Propulsion or EPS. So for we pretty much
just power, just electrical power.
So just solar panel. So we have 3 U's on 3 U of solar panel on this side, so giving about 17 volt, 1 U here on both sides, and 2.5 U on the back, 1.5 U here, and then somewhere about 20 watt hours of batteries, I think, as our baseline. And our instruments are not very hungry, and our power budget is quite large right now. Answer your question, Jim?
Yeah. How sensitive are you to thermal? I mean, do you have a range? What's the range, the operating range that you have to stay in?
So I think the upper range is pretty. I mean, I think it's. I didn't put on this slide. I have it in the PDR slide. I think the largest one is somewhere about 60 degree. The top range, I think we're pretty good for the top range. I'm not too worried. The bottom range, so I think the closest one is, I think, the ADCS and the batteries that cannot go much below 0. So you probably don't want to be much below 0, and we are below 0 right now in the night side at the end of the eclipse. And so most likely we're going to put some heaters there. Also depends. I mean, that's a simulation we did almost a year ago by now. Also depends what you leave on and what you don't leave on. I mean, obviously, everything on gives you some heat at this stuff. So the onboard computer is on, the radio is on. This is the radio is on the biggest heat source. It does change, but I think the most worry part is the night side, making sure we don't get too cold for some of the electronics to not work anymore.
What did you say the types of particles that the CubeSat will be able to measure? And is it electrons and oxygen neutral?
So yeah, so the electrons is direct. I didn't spend too much time on the instrument, but so the electrons, what we're gonna do. So it's energy ARPA. So it's we're gonna put a bias voltage on some of these plates here, and so that's gonna only allow some of the electrons to come through. We're gonna go through 6 voltages every 125 100 milliseconds, if I remember correctly. So this is directly measure electrons. The top voltage will be 150 volts. So we're gonna measure electron between somewhere around 10 and 150 electron volts. The oxygen, we don't measure it directly. We measure emission in the 130 nanometer band. So there's 2 bands here from oxygen 1. I forgot, one is 3S, 1P. I forgot which one exactly they are, but there's 2 bands very close to each other from oxygen, neutral oxygen. And so we're going to measure the UV light looking up. That's kind of the new thing at this. That was from the Renew 2 rocket ID. So we're going to looking at UV light that is generated primarily by oxygen. I think there's some N2 line the same, but there should be very little N2 at this altitude. And so then it's a bit more complicated to actually get the oxygen from that. So we're gonna get is a curve like this one. And you can see, I don't know how much you can see my mouse, but those actually here, the spikes here in the UV emission actually are enhancement in oxygen that ReNU2 measured when it was crossing through a part with a lot of electron precipitation. So we'll see something similar to that. We'll see enhancement of the UV light associated with oxygen. And so that's, if we actually want to get the oxygen density, it's quite complicated, probably requires some advanced atmospheric modeling, but we'll be able to characterize the oxygen at least, like saying, you know, we see an enhancement as compared to last orbit, or we see an enhancement as compared to a few minutes ago.
How would you go about like going through a calibration process for the like measuring oxygen? Because you explained the electrons, the beam, like in chat back.
Yeah, that's a good question. So we're gonna go, it's really about, we're calibrating the UV. So we want to know how much voltage or current we get in the instrument for a given UV source, for a given UV rarely brightness. And so then we can know exactly, because at the end of the day, we measure the current created by this PMT. So we want to know exactly what is the calibrated brightness we will saw in the sky at this time. That is not directly the oxygen. To get the oxygen from this, you then now need to run some kind of model of the atmosphere with kind of taking correction, the integrating over the line of sight or things like this to know how much oxygen there is. But we might or might not do that, depending on how much data and funding we get for the science. But we should be able to, with calibrating UV light, to be able to say if there's more or less oxygen, because it could be directly proportional, or not proportional, directly one-to-one relationship. No, brighter UV light means more oxygen.
So there are some questions online too. So let's start with Eric. You can ask your question.
Yes. Yeah, I also had a question about the oxygen measurement that you mentioned that there's a significant inversion that you will have to do in order to get density. I was wondering if velocity and temperature had any significant effect on the measurements, or whether density was the dominant variable here.
So yeah, I don't think velocity does. I don't know about temperature precisely, but I think really it's primary density. Obviously, it's a bit temperature should have some effect because those are this is oxygen which have been not on the ground state anymore. I just want to point out that we're very careful to not propose or not promise to measure the densities. We want to characterize the densities. That's why this word was chosen, is that while we will most likely measure precipitating electrons, we'll actually only characterize the neutral density. So I think when you get this UV, calibrated UV light brightness, that actually does characterize the neutral density from oxygen. I mean, the key issue is that to know which one of these two lines, which we're not going to be resolved, this two line, because our filter is going to be about 20 nanometer, which is more than the distance between the two bands. So there's quite a bit of other lines happening in this around 130, 140 nanometer. So it is quite a complex thing to invert it. Sorry.
Okay, thank you.
And now we have a question from Eberhard. Sorry.
Yeah. Hi, Noé. Thank you. That's an excellent, challenging and student-centered program. I have a question and a comment. So my question is along the lines of where does it connect and enhance IMAP? I suppose what you could use from IMAP is measurements of the solar wind monitoring suite on there. the ENAs from IMAP, they're not useful here because we're not looking at the magnetosphere. But my comment is we are doing everything we can that IBEX is still operational in the first and second year when we want to do cross calibration with the IMAP ENA sensors. And that presents a good opportunity here for combining IBEX ENA measurements with your in situ measurements of the cusp, because the cusp has been seen in IBEX ENAs, and you could make use of that. So if you want, I can point you to a couple of papers about that. So
yeah, no, thank you. I hadn't thought about the magnetospheric ENAs. So kind of I assume, or I decided not to take the time to explain what IMAP does, but IMAP really, as for the people who don't know, has kind of two main components. So the mother mission of this, which will launch in about 2 years. One is looking at neutral atoms, energetic neutral atoms, ENAs, coming from the kind of the edge of the solar system. And the other one is kind of providing solar wind monitoring a bit before Earth. And as Eberhard said, the key connection between 3UCubed and IMAP is with the L1 monitoring, so space weather monitoring, solar wind monitoring. And really the key driver of the cusp location is a magnetic field, not BY and BZ, both BY and BZ primarily, where you will see this larger electron precipitation, typically between 10 and 200 eV, when BZ is slightly south, or sometime when BY is also consequent. And so we'll try to kind of connect, I think, past every 100 minutes on average, we should be able to connect quite significantly. So geometric storm, or even the BY and BZ conditions, to electron precipitation in the cusp and to atmospheric upwelling. So that's a main connection. So when I was talking about in the very beginning about connecting IMAP measurement with IMAP stone collaboration, that's really about looking at the magnetic field and solar wind measurement. Potentially, some of these electrons that the cusp I think actually are from the solar wind themselves, because that's the idea of the cusp. The cusp is a location where the solar wind has access to Earth's upper atmosphere. So we could actually look at some of these electrons. These are not at magnetospheric origin, but some of them could be of solar origin. And then they'll also be measured by other instruments on IMAP. But then, yeah, I knew that there was a plan of cross-calibrating IMAP and IBEX, but I hadn't thought about the consequence for magnetospheric ENAs. But yeah, that keeps us in mind. And yeah, let's you and I talk maybe about it. Thank you.
And then the final question from Ben.
Noé, very nice talk and very nice program. I just had a question for you about the undergraduate involvement later on in the mission. Are you planning to have a lot of undergraduate involvement in data analysis, or will that taper? And it's mostly like in the design and building phase that you're getting the undergraduates involved.
So that's a tough question to answer, because again, we're quite a weird program. Okay, let me take a step back. So most student collaboration get funded through the main mission, but what we decided commonly with Dave McComas early on is that the student collaboration of IMAP is getting money separately from IMAP. So long story short, but the consequence of this is we got funds to build this, but right now I don't have funds for the data analysis part. I budgeted it, and so NASA knows how much money I say we'll need, but we didn't receive it, or it wasn't promised. So I don't know exactly. My hope is that for sure students should be involved in the operation. So kind of the ground operation, the commanding, and all these things. I think there will be definitely fewer students involved in data analysis than we have now. I think we have about 10 students at UNH right now, and probably 15 between Sonoma State and Howard. And we're not going to have 10 students or 20 students doing data analysis when this is launched. So it will taper down. But I'm hoping we can have a decent number of students actually doing kind of the engineering part of the operation, kind of housekeeping and instrument, and then hopefully the extended phase concept of operation. But I don't. So short answer is that I don't know.
Okay, thanks.
Okay, so I mean, there are like around 5 minutes left, so if you want to briefly talk about the.
So I can show you one slide, kind of just some general ideas. I have a lot of text in that slide, so I just speak about it. That's the totally changing thing. It's talking about Class D missions because I just submitted the specs, but it's related to CubeSat in some sense too. And so Class D mission is the smallest mission that NASA funds, which is less than $150 million, which sounds a lot if you're an undergrad, but it's not a lot for a space mission. And NASA has really tried recently to release the Bocan as the AA to kind of make it easier to do Class D. And not many, I mean, people are aware of it, but people don't realize how much it is. So this is a streamlined document that allows you to kind of use different level of quality assurance of how much cut sport you can use. Pretty much you can do a CubeSat as a Class D in some sense. And that's makes this Class D very different and to me very attractive. Partially also because there's a lot of, I'm sure most of you know the new so-called new space, all these companies that build launcher or build satellite from BCT, Millennium, Rocket Lab, Terran, Tyvek, and other. There's a lot of companies now which actually do satellite for cheap. By cheap, I mean you can buy a decent sized satellite, maybe a washing machine size for a few $1 million. And on a Class D, streamlined document, you can actually buy this off the shelf, put your instrument on it, and launch it. And that's something you cannot do for bigger mission. Because for bigger mission, you need to have all this part being space graded, being radiation hardened, being Q&A'd at an extreme level. If any of you are involved with IMAP main mission, you'll know how much Q&A and requirements there are on bigger mission. And so I was just kind of my fourth point here, but I played the game of I designed a 4 spacecraft mission Class D, so buying a satellite off the shelf in some sense and putting an instrument on it. And I put myself, what if I want to make it a Class C mission, meaning that I cannot have off-the-shelf components. If I do exact same mission, nothing changed. I take the exact same mission, I just say, okay, now I want to have the full level of Q&A and build everything myself. The mission goes from 150 to about $500 million. The exact same mission, nothing else changed. And that's some of the things happening now in the decadal is very similar missions to the one I proposed, but slightly more instruments, slightly more complex that moved into Class C and suddenly go from $150 million to $600 million. And I think the main part is how much does it cost to build a satellite? If you want to build satellite yourself, or you're not going to do it, but if you want Applied Physics Lab or JPL or NASA Goddard to build you satellites, they're not going to build it for 2 or 3 million. They're going to build it for 25 to 30 millions per satellite. And that does change the game totally, just because of engineering time and so on and so forth. So I just wanted to put some thought in people in the room here, saying that SMECs are fundamentally different from MIDEX, because MIDEX are Class C. Also, they can be part of Class D, as Helioswarm is doing, and I think that's a smart thing that Helioswarm did. But I know a lot of people involved in SMEX been asked all the time saying, "Oh, are you going to do a mid-X next?" And my point is that I think a true valuable SMEX cannot be transformed into a mid-X. It shouldn't be able to be transformed into a mid-X. And the last thing I want to add on this is that NASA is taking a lot of risk now, and this is pretty recent news from last week or from maybe a few days ago even. Escapade, which is this 2 spacecraft mission to Mars, which is a 2 spacecraft mission for $55 million, which is really cheap for a Mars mission or anything. NASA just manifested them last week on New Glenn from Blue Origin, which is a rocket that has never launched yet. So most likely it will be a maiden flight. And so I'm sure NASA got like the cheapest quote from Blue Origin because it's an unproven rocket. I'm sure they give them a huge discount. But so that's a huge risk in my head. I mean, if I was a PI, I haven't talked with him yet, but I will talk with him about it soon. I would feel quite scared about it. Spend 3 or 4 years designing a mission, and you're going to launch it on a rocket that never launched before. But that tells me that NASA right now is ready to take risk on launchers, which I don't think we scientists and engineers are taking yet for smaller missions in terms of the design yet. So just the few things I wanted to put here, just kind of talking about when you design mission, mid-X and SMEX, don't think of them interchangeably. And I'm not involved in that part of the decadal survey for your physics, what's going to happen in the next 10 to 15 years. But I really hope that NASA continues and really make it clear that SMEX are what they are on paper, very high risk missions that you can literally take off the shelf. And when you put off the shelf satellite, you can really do a lot of science for a much lower budget. So that's why you kind of connect with CubeSat. That I think things are happening with CubeSat now that should we translate into mission opportunity and smaller class D mission. I'll stop there.
Thank you very much.